Now, the way that we can determine whether a function is even or odd algebraically is actually by using the definition that we had up here and just doing that. So, and there's a little step-by-step guide to help you get started if you're not exactly sure what to do, but it says how to test for even and oddness algebraically. Step 1, it says to plug in negative x into f. In other words, simplify f of minus x. And the reason we want to do that is because notice in both definitions, they both have f of negative x in the definition. And so we kind of want to see, well, what happens? Then step 2, what it says is if you get f of x, it's even. If you get negative f of x, it's odd. And again, that makes sense because that's exactly the definition. Even functions, if I plug in negative x, if I get back the same thing without the negative, it's even. If I get a negative on the outside, it is odd. And it says if you get anything different, the function is neither even nor odd. And this is a little different than integers, because with numbers, like whole numbers, they're either even or odd. With functions, they could be even, they could be odd, but sometimes they're neither. They're only even and odd when they have very, very specific symmetry to them. And if they don't have symmetry, they're neither. End of discussion. Now let's look at this example. And we could again graph this to figure it out, but let's just try following the step-by-step procedure. So step 1 would be to plug in f of minus x. So basically what we're going to just do is write f of negative x. And to do this, well, remember to evaluate f of x, you're just going to change x to negative x. So in each instance, like say I was doing f of 2, I would change both those to 2 and do math. But here, I don't actually know my input, which is what's a little different. But what I do know is that I want to substitute in negative x in for x. And so reminder to use parentheses when you're plugging it in, because the negative should be, in this case, the entire x is cubed, and we're plugging in negative x into the entire x. So that whole negative needs to be cubed and plus a negative x. Well, what I have here is negative x cubed, which is negative x times negative x times negative x. And we all know that 3 negatives multiplied together stays negative. And adding a negative is the same as, whoops, and that should be x cubed because I had x times x times x. And over here I have plus a negative x, which is just the same as minus x. So what I'm left with is negative x cubed minus x after simplifying. And the question is, well, what do I do from here? But notice that this function is exactly the same as what I started with, but now the whole thing is negative. And I could technically factor out a negative, which would leave me with x cubed plus x. You might wonder, well, couldn't I also factor out x here? Yes, but you'll see why I don't want to in this case. But because if I factor out the negative, what I'm left with is negative x cubed plus x. And x cubed plus x was the original function. And so what I've just wrote is, well, I have negative the entire f of x. And so what I've just shown is that f of negative x is equal to negative f of x. And by the very definition, that is what an odd function will do. So that is how I can conclusively show the function is odd, because I've shown that f of negative x is equal to negative f of x. Or, I don't know if that was kind of hard to follow or a little bit, a bad way of explaining it. Basically, when I'm applying a negative on the inside, what should happen is the entire function should change to a negative, and that should be the net effect. And that's how an odd function will always behave. If you plug in a negative, you end up getting a negative on all terms. Now, an even function will be exactly the opposite of that. When you plug in a negative, it should just disappear and cancel out. And a function which some of them change and some of them don't, or something else happens entirely, is generally neither. So let's look at number 2. Also, another way you can check when it comes to polynomials being even or odd is if all of the degrees of all of the terms are all odd, you're going to have an odd polynomial function. And notice since this was degree 3 and degree 1, those are both odd, so what we end up with is an odd function, because cubing, right, the negative will stick. First power negative will stick, and that's what made it odd. And in this one, notice that since 6 is an even degree, and actually a constant is technically a 0 degree term, these are both even, which actually implies that this should be an even function. But let's prove it algebraically. And again, you want to start by, as the instructions say, plugging in negative x in for f of x. And that would just mean all the x's are going to change to negative x. Again, and make sure to use parentheses because here I have x to the 6th. I want to make sure the whole thing is being raised to the 6th power. And while now examining what I have, well, 1 is not going to change because that was a constant and not dependent on x at all to begin with. Now for x to the 6th, well, now I'm going to have negative x to the 6th. So this would actually be negative x times negative x times negative x times negative x, etc. So this would actually be 6 negatives all put together. And well, I have a 7th negative out here. So a total of 6 negatives, those are all going to cancel, right? Because a negative to an even power will always cancel out. But I'm going to have another negative left over. So a total of 7 negatives leaves it at negative. And that's going to leave me with 1 minus x to the 6th. In this case, that negative canceled out because it was even. So essentially the negative did nothing. The negative, I sometimes say the negative got eaten. And really what I'm left with was exactly the original function, 1 minus x to the 6th. Nothing changed. And that's exactly the idea behind an even function. When I plug in a negative, it doesn't make any difference. It is the same as whether I were to plug in a positive, like a parabola. Because like a parabola I'm squaring, it doesn't matter whether I plug in positives or negatives. They're both going to give me the same positive answer because you're squaring. And same with 6 powers and 4 powers and so on. Those are always even, and those always will have the same symmetry that I described above. So there's various different ways you can determine. That's sort of what I wanted to wrap up with. And knowing that a function is even or odd tells you a lot about what it will look like. And in, say, trigonometry, you have functions like sine, which are odd, cosine, which are even. And those are helpful tips which can sometimes have very meaningful results. But I'll leave the last couple for you to check for yourself. And also, with number 3, it ends up being neither. You can tell because some of the terms will change signs and some of them will not. So also, to sort of wrap up, an odd function, all the terms will change signs. An even function, none of the terms will change signs. And when it is neither, some of the terms will change and some of the terms will not change. Or another way you can then verify after is by using the graph. You can graph a function in your calculator, examine the symmetry to see, well, an odd function should be sort of like this, where it's the same and flipped, whereas an even function should look the same on both sides.